So in today's video, I'm going to talk about using principal component analysis. And basically the idea in principal component analysis is we're going to actually redefine the axis in such a way that we can plot multidimensional data. So let me just probably start off with an example. So imagine we have x is equal to np linspace, and maybe I'll go from -1 to 1 and then 10, and then y is just going to be equal to x plus, we'll put a little bit of noise, like 0.3 rand normal of 10. And then I'm going to do PLT plot of x comma y with just a dot. We'll color it red, and we'll make the line width equal to 3. And then I can just do PLT show. And what I have is kind of a plot. And what you might notice with this plot is basically what we have is y is equal to x. So here's x down here. Here's y over here. But if you see that the two variables are strongly correlated with one another. So they're not perfect because we added a little bit of noise, but we see kind of variability. And if you think about this, the data, even though it's plotted in 2 dimensions, so each value has an x and a y value, in reality, most of the information is contained in 1 dimension. And so you can imagine if we could rotate the axis. So if we rotate this in such a way that this line kind of comes down here, we can basically take 2-dimensional data and represent it as 1-dimensional data. And that's kind of the idea on principal component analysis, is we kind of come up with a coordinate frame of reference in such a way that our data, we can represent multidimensional data as 2-dimensional plots. So just kind of to emphasize this point, so I have PLT plot, and if I just plot x and x, and let's do line width 3, color is equal to blue, right? You can think about the blue line as defining 1 dimension. And if we think about this as the 1 dimension, and then our other dimension will be orthogonal to it, right? So it'll kind of cross over here. In that representation, most of our data actually plots on this one axis, right? So if I want to plot the other one, I do PLT plot. Let's do x minus x, line width equals 3. And then color is equal to blue. Let's make sure I get this one right? So here we have our 2 plots. Both of these axes, so if I did PLT axis equal, right, you can see that the blue lines represent kind of a new coordinate system, right? They're orthogonal to one another, like a Cartesian frame of reference. But in this way, you see most of the data actually varies along one axis, and we see very little bit of variability along the other axis. So most of the movement is along this axis, and then a little bit less movement is about this axis. And PCA, which stands for principal components, we can think about these as the principal components, basically defines a new kind of orthogonal coordinate frame system that makes it such that the first dimension captures most of the variability of the data, and then the next dimension is the one that captures the next most variability in data in the third dimension, and so on. Hopefully that's a little bit clear. But if we want to do this, what we could do is we could define just z. And we're going to do np column stack. And then I'm just going to column stack x and y. So if I take a look at z, it's just basically creating a 2-dimensional matrix where this is the first coordinate and this is the second coordinate. And then what I can do is define PCA. So for principal component analysis as PCA. And then what I can do is do PCA fit of z, right? And what this is going to do is determine the new coordinate system. And then what I can do is I can type a big C, and I can do PCA transform the data set. So here we're going to transform our original data set, which is in kind of these XY points, and then kind of represent them on our new axis, which is basically going to be this axis and this axis. So if I proceed with this, I can go ahead and plot this up. So I could do PLT plot. And what I'm going to do is just plot z of tilde, comma 0, right, which is the first dimension of the axis. And then here's kind of the second coordinate. And then I'll put the red dots. And maybe I'll do line width is equal to 3, color is equal to red. And then what I'm going to do is do PLT plot. I'm going to do PLT axis. I'm going to make them equal. And then I'm going to do PLT shell. And basically what we've done is taken our original data set, which is kind of along this diagonal, and then replotted it on this kind of new coordinate system, which is what the PCA determines, which is our kind of the best coordinate system to represent this. And what you see is that basically most of the data, it's basically all in this dimension, and we see less variability in this dimension. And to make it even more extreme, like if I take out all the noise, right? So now I have my data points exactly along this axis, right? So there's no noise. And then if I do my PCA transform, you see all the points now on our principal axis, and they lie there. And we see no variability in the other dimension. And so basically PCA, the way I think about it, is about a coordinate system, in which case if we rotate the coordinate system, often we can take n-dimensional data and represent it quite accurately with maybe 2 or 3-dimensional data. In this case, we're taking a 2-dimensional data set and basically representing it as points on a line. So let's just add back some noise just to make it a little bit more realistic. So 0.2. So we have some variability, and then we're going to run it here, and we see the variability in the dimensions. There's one other key variable with PCA, which we can do print, and what this is going to do, PCA and explained variance ratio. And what this is going to do, what did I do wrong here? Oh, I forgot the underscore there. And what this is going to do is give me 2 numbers. And the first number is telling me how much of the variability is represented in the first coordinate. And we see that 99.4% of the data is represented in the first coordinate. And then 0.5% is represented in the second coordinate. So the variability, how much it moves, most of it's all in this new kind of x direction, and very little of it's in the y direction when we rotate the axes using PCA, right? And these numbers are always going to sum to 1 because it's going to be 100% of the variance, right? Whereas in the original coordinate system, we see that, for each data point, the data points vary both in the x and y dimension, but by rotating the axis, we get all the variability kind of in the x direction, and we see very little bit of variability in the y direction. All right, so how is this useful? So let's consider data is equal to load iris, and we're going to say x is equal to data dot data, and then y is equal to data dot target. What did I do? Load iris. Did I not? Let me make sure. Oh, I forgot to import it. So what do we have? From sklearn dot datasets. Let's import load iris, right? And one of the things, if we look at the shape of x, right, what we see is that x, right, so in this case we have, these are the parameter values or the measurements for different flowers, and y is the type of flower that it has. Basically we have 4 dimensions for this data set. So this makes it very hard to kind of visualize kind of the data that we're looking at, and that's really where PCA comes in. So what we could do is do kind of PCA is equal to PCA, and then we could do PCA fit, and we're going to fit it to our x, and then what we're going to do is z is PCA dot transform of that x variable. So here we're fitting the PCA model to our data, and then we're just transforming the data. Sometimes you'll fit it to one set and then transform another set, so it kind of gives you some freedom. But if we look at kind of the variance ratios here, and that's kind of the key thing, right? So we've changed the coordinates of the data, and we see that the first coordinate represents 92% of the data. The second coordinate represents 5% of the data. And then if you look at the third coordinate, that's like just under 2% and 0.5%. So basically, if you think about plotting just the first 2 dimensions of your data set, you see that you're basically capturing, if I think about kind of the sum, right? If I do sum of this variable and I do the first 2 data points, what I'm capturing is 97.7 or 97.8% of the variability in the data set. So that means we can represent, even though this 4-dimensional data set, really we can represent this as a 2-dimensional data set. So to show this, we're just going to do PLT plot. And then we're going to do z tilde comma 0, and then z tilde comma 1. And here's kind of the points. I'll do line width equals to 3, and then we'll do maybe color is equal to red. And then I can do PLT show. And here's kind of the representation in 2 dimensions where we're capturing actually most of the variability. 97.7% of the data is being represented in this plot. Now it's probably a little bit easier. We want to color it, for different colors. So, if we come down here, we look at kind of our Y value, right? Y is a number that's either 0, 1, or 2. And so what we want to do is color these data points based on kind of, whether it's a 0 class, a 1 class, or a 2 class. So it's pretty easy. So we could just do Y is equal to 0 here, and then Y is equal to 0 there, and we'll make that the red dots. And then we can come down here. We can do Y is equal to 1, do Y is equal to 1, and maybe we'll call this blue. And then we can plot up our third point, and we'll maybe make this equal to green. And then we plot it up, and you actually, when you see this in the 2-dimensional plot, it's very clear the separation between the data. So the red points are clearly separated from the blue points and the green points. And then the blue and the green, right? Basically, if you were to draw a line here, we can separate or classify these data. So PCA you can think about as a data reduction technique, right? So we initially started with 4 dimensions. We changed the coordinates such that really when we just plot the data in 2 dimensions, we actually capture most of the data because the data is not truly filling out 4-dimensional space. It's actually mostly populating, basically it would be a sheet or a plane in 4-dimensional space, or 2-dimensional manifold is what they would, or subspace would be a better word for it, in kind of 4-dimensional space. And that's really what we're taking advantage of PCA, is kind of getting this kind of separation out. Now, once you have this, of course, we can, classify based on PCA, right? So we can do different kinds of classification data. And I'll cover that in the next lecture. But the key thing about this is that we have, basically we're doing a coordinate transformation. And PCA is really about determining these coordinates and telling us how much information is contained in the first coordinate, how much information is contained in the second coordinate. If we had a third coordinate, it would be coming out of the screen. And that's kind of the basic idea of PCA. And this will make it much easier to kind of look and analyze different, kind of visualize some of these data sets that come with, this sklearn, where you actually have multiple variables, but we want to be able to visualize it. And PCA is one of the stronger techniques that we can take 4-dimensional data and basically represent it as 2-dimensional data and basically capture all the information. And then we can design our algorithms based on kind of the projected or reduced data set. Hope that's clear. If you have questions, please post them to Piazza or put them to the discussion section. And I'll do one last thing before I run. So often what people do is they'll do PLT like X label, and they'll do like PCA of 1. And then what they'll do is like percentage, let's do 0.2F. And what they'll do here is they'll actually put in kind of the variance ratio. And so in our case, it's going to be, let's do it percentage. So we'll do 100 times, I got to probably put this in parentheses, and we'll do 100 times coordinate 0. And then the y-axis will be our second PCA coordinate. And I think I'm missing missing a parentheses. Well, now I have an extra one. No, that's correct. Here, and then we do PCA 2 here, and then we do our variance ratio 2. And then typically, that is not right. 100 times PCA 1. That's my Y label. That's why it's wrong. And we're seeing our PCA 1 coordinate, we have 92%. And then our PCA 2, we have 5%. And with that, I'll stop. And again, if you have questions, please post them in the comment section. Thank you.